start the session. So, in case of this electromagnetic field theory, we have most we have completed the electrostatics and magnetostatics. Then we move to time varying fields. For time varying fields, we have derived the expression for the electromotive force. Then we move to Maxwell's equations. And then from Maxwell's equations, we have moved to the electromagnetic wave propagation. And by solving the Maxwell's equations, we have seen that what are the waves can exist in different mediums, that all we have discussed. And by the way, we have completed module 3 and module 4. And this topic, that is the electromagnetic wave characteristics 2, is belongs to this module 5. Okay, so the module 5, it looked big, but it is very simple one. Like, we are going to see there are two types of boundary conditions. One is the normal boundary and oblique incidences. When the wave is traveling from one medium to another medium, what are the changes it may happen in the wave, and how this medium is going to react for that. And also, when the wave is incident on the medium, another medium by oblique incidence, that means it is not perpendicular with respect to the surface of this two medium. Then we will see some interesting facts. There are some practical applications also available. And at the end, the topic covers with pointing vector. But the pointing vector is supposed to be studied well before this normal or oblique incidences. So I will start with the pointing vector, pointing theorem. Then we will see how this boundary conditions works. So we already studied the Maxwell's equations, and you will wonder that this so-called wave equation derived out of Maxwell's equation for the basic static conditions itself. Therefore, this wave equation, which are actually derived or which are taken out of the solutions of Maxwell's equation, is all like very natural process. So first we have solved the two equations. Like for the plane wave, the conditions to achieve is there should be source-free isotropic homogeneous medium. So after considering that, we got these equations. So if we consider this equation 1 and 2, then these two equations supposed to be simultaneously solved. So for this, we have to put this equation in this, and this equation supposed to be substituted here. Then we will get the expression for electric and magnetic fields. And that is what we got it here as a Helmholtz equation, or popularly known as the wave equation for electromagnetic forces. And this further we derived, and we got two conditions. One is forward traveling wave and reverse traveling wave, or backward traveling wave. When we add together at the same operating frequency and the phase velocity or the phase constant, then they will add each other and we will get the standing wave. We will study about the standing waves maybe in a particular given medium. For instance, in transfer line theory, the standing wave is going to come a lot. So maybe at that time we will discuss about this. So we have considered how this wave travels in a given space. And in case of plane wave, our condition is the wave travel with respect to time is always in a constant rate, which we given as a angular frequency. Then we studied this how this wave could exist in different mediums, like in a lossy medium. And in the lossy medium, we have described the new phenomena with conductivity, and thereby it introduced the attenuation constant, and also differentiate with the phase constants. And we have calculated both the values, and by this we can see the relationship between the electric and magnetic field, how they converse from one to another. That is described by the ratio, what we refer as the wave impedance, or the intrinsic wave impedance of the given medium. That is purely described by the three fundamental quantities, like sigma, and then the epsilon and the mu. while this omega is a relative term which describes the rate of change of the wave with respect to time, and which we call as the angular frequency. This angular frequency also coming into the picture. So we can easily understand that at one particular point, this wave, therefore this wave impedance eta is subject to frequency. So this value can increase or decrease, whatever that could be a possibility. So in order to achieve a particular impedance for a medium and for a particular operating frequency, we can choose this epsilon, mu, sigma, all these things we can choose. Therefore, we have to choose the right medium for that. For instance, you want to oppose a particular wave to within your particular box. Let's say you take your mobile phone and you have to cover it with some high impedance material. So the material is supposed to show very high impedance. Therefore, what this value is supposed to be? Actually, we know that the outside free space is having 377 ohm, but I want to have very high value. Let's say I just want to get 1000 value, and this system should not be affected by the particular operating frequency. So substituting this frequency and the impedance, we can get the ratio of the sigma and mu and epsilon. By choosing one value, we can get the other value and then we can design such a material. Therefore, if you coat this particular material, the special material which is going to show the wave impedance of 1000, which is actually very high. So therefore, when the wave comes in, it will be dissipated before going to the actual structure or the mobile phone, and the thickness, whatever that you want. If you want it in micrometer, then we have to choose the all the so-called mu, epsilon, and sigma accordingly. So it is definitely possible within the scope of the material science. Then we also studied the effect of the alpha and the another important phenomena, that is loss tangent, also we have studied. So these all phenomena like alpha, beta, and the loss tangent, the impedance, all of them are highly connected. Then this is for the very general case when the medium is lossy dielectric medium, and here when we give some special conditions, for example, if it is a lossless medium, then obviously we will get the conductivity is almost equal to 0. So that is what the meaning of that. That is not even approximate. It is equal to 0. In that case, you will get alpha equal to 0. Since alpha equal to 0, the wave amplitude will not be affected by any means. So it is keep on going to travel for infinite distance. But there will be a phase difference between these two. Yeah, of course, there is since the sigma is equal to 0, then the loss tangent is also 0, and the so-called the phase term is also going to be 0. If the phase term is equal to 0, then there is no phase term here. There is this eta, the angle term for the eta is equal to 0. That means the uh, both these electric and magnetic field will be in phase. Also, we have seen the condition in the free space. Free space is another lossless medium, but it is having special condition that this epsilon r equal to mu r equal to 1. So, and you will get a special value that is 377 ohm. My professor who taught me this RF and microengineering, he tattooed this 377 ohm. You can understand that for him how important it is. So this same thing if we apply to a good conductor. So the good conductor obviously will be having often referred as perfect conductor, will be having conductivity as infinite, and within the medium, within the good conductor, always there should not be any electric field. However, within the induced electric field itself, if we consider because of the uniformity, you'll get epsilon r equal to 1. And we can't argue that it is not a magnetic material. It could be a magnetic material. There are several metals, they behave as a magnetic material. So this still it is not equal to 1, or it is greater than 1, we can say that. So when we substitute all these quantities here, then you will get the expression for alpha and beta, both are equal, surprisingly, and which yield this phase of that term, that is actually theta eta, is going to be 45 degree. So, which in other words, we can say that the electric and magnetic field will be out of phase about 45 degree. And sometimes this is the reason for fast fading of uh, the 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 field which is entering into the medium. So from the surface of the metal, before it is going towards inside the metal, it will be its amplitude will exponentially will decay. After certain point, it is going to saturate. However, within a given delta distance, the amplitude will reduce by 37%. That is often referred as skin depth. And this is the term with respect to frequency also. So as frequency increases, this value will go very high. And we already studied about that. For instance, why metal is stopping the high frequencies. This is one of the very important reason. While dielectric materials, they won't stop it because their conductivity is very, very less. Since the conductivity is very, very less, we could say that the so-called the skin depth will be very big for them. Sometimes in terms of meters like that it may come. So within the scope of the small thin films, so this del value is highly negligible. So they we can see that these materials are not going to affect the amplitude greatly. But in case of metal, it do that. Now, these are the cases what we have studied in terms of electric and magnetic fields, how they propagate in a given medium. And based on this concept, John Pointing has come up with one of the most influential term that is called power. So how this electric and magnetic field, which are sustained in a particular medium, how this is going to react to the medium, or it is going to dissipate the energy, all can we calculate or not? It is possible to calculate, but provided we need to get the expression for electric and magnetic field. It is quite same as that of the power is equal to V into I. So we know that V square by 2R can give the average power dissipated by the resistor. We can easily calculate. So we need such a very similar expression. Since both are vector, then you will get a resulting vector, and that vector is going to tell how this energy will be dissipated or propagated, or it is supplied to another material, or within the scope of the material or the conductor, whatever it is. So how this power will be transferred from one place to another place. So to answer that, it seems like Maxwell has started this work, but due to the illness, he could not follow that. But his fellow student, otherwise his immediate co-worker is John Pointing, and he developed that. I think Maxwell I died in 1864 or 67, I think. No. He died about in 72 or something. By that time only, I think Einstein was born. So by that time itself, Maxwell could not provide his contribution, but John Pointing actually he has developed a lot in that. In fact, it seems like how the energy is traveling from sun to earth, such a heat energy, as well as this kind of magnetic field, how it is traveling. All these things were largely described by John Pointing only, and Maxwell's equations could do such a description about that so-called the governing physics. And I think John Pointing also largely influenced J.J. Thomson, and and I think John Pointing was the co-worker with so this J.J. Thomson to describe the behavior of the electron when it is available in an electric field, when it is available in a magnetic field. We know that in electric field it will be accelerated. In magnetic field it will go in a circular manner. But when we apply both together, how it will go? And parallelly, many other works were going on, including the works of Henry. Lawrence and all, they have worked parallelly upon this same problem. So John Pointing, by that way, he is one of the great contributor in electromagnetic field theory. And interesting, we will see some more interesting concepts in French field theory, considering the Pointing's work. Okay, so how to do that? For this, to achieve this particular one, we need to find a particular identity. So this identity in the differential calculus is described in this way. So you can see here, if we have del dot two vectors, then you will get these two quantities will come. This vector identity by rearranging this expression. When you bring this here, then you will get this expression. When you bring this one and rearranging that, you will get this expression. So in order to get the del cross A B, and by the way, we can integrate and we can isolate this so-called the quantity. Two vector cross product we can easily get. By the way, we supposed to get this term, and we very well know that this these two terms, if we have A equal to magnetic field and B equal to electric field, we can easily see that it is directly available in Maxwell's equation, and that too in the time dependent form. What actually often referred as curl equations. So when we take curl of electric and magnetic field, we will see that the manifestation in the orthogonal property, that is corresponding magnetic field or electric field, will come with respect to time. And when we supposed to substitute one on another, for this we are going to multiply the first equation by magnetic field and the second equation by the electric field. Then you got very similar description here. So we already substituted this A as a, if we see this equation, this is nothing but electric field, and this is going to be the magnetic field. And this very same expression is available here, and which is equal to this. Okay, so if we keep this term as a left hand side, this term as a, this term is the right hand side, and this term, the corresponding this term will be in the right hand side. So when you keep that, then then both the side it is equal. So that is how it is being described. So you can see here. So this term is taken and placed over here. So you can see that when the electric field is placed inside, you will get the square term will come, and then this particular term. So this particular term is going to be, it is available here, and when we substitute that, we can rearrange this expression. This is actually a bit lengthy substitution. For big detailed derivation, you can refer the book Sadiku itself. It is available, and it will be available within the pointing theorem itself. You can see that. So we got this expression. We supposed to rearrange that. When you rearrange that, you will get this term. Remaining all term, we can move to the other side. You will get the negative term because of this, and this term will become positive. So you got this expression. Now, in order to calculate the total power, which is due to this the oscillating electric and magnetic field over the space, we're supposed to take the integration. So when we integrate that, we will integrate the other terms too. And by the way, this we can easily calculate by closed surface integration by Stokes theorem. So when we apply the Stokes theorem, we have to apply the divergence theorem in order to convert this value to surface integration. By this, you will get. So provided this also a vector, this total cross product also going to be the vector, and this two result will give surface integration, and the surface will be having its own normal. So the resulting one will be in the normal itself. So that is what we have to keep in mind. And right hand side, there is no change in the value. So what this actually equation means is this term in the left hand side is going to describe the total power leaving the enclosed surface to cover the value. Okay, so that is nothing but the total power. Okay, and in this, if this is the total power, there are then the right hand side also supposed to be power. But what these powers are, nothing but two different powers. The extreme one, which is don't have any time dependency one, and it is going to tell how the power is dissipated from the medium. And therefore, the remaining power supposed to be available within the medium itself, and that is the stored power, and which is having a differential term. Therefore, this inclusive term is going to be the energy. So the rate of change of energy due to electric and magnetic field, and within the given volume, it is. So in other words, what is the meaning of that is nothing but a medium. Okay, the medium has its own property like sigma, mu, epsilon, all these things, and there is the existence of electric field, and the corresponding magnetic field is available. One is available in x-axis, therefore another one will be available in one y-axis, and the wave is actually traveling in the z-axis, and it is going to travel with the constant rate of omega with respect to time. So that is nothing but omega t. Now, this is now when you calculate the cross product of electric and magnetic field, then you will see that the total power, and the total power is divided into two. One is the power dissipated by the wave, and this may be due to the heating of the particular medium, or due to the conduction current. It can leave the structure itself. By any means, it is going to be lost. So that is what actually described as the power dissipation. And on the other hand, with respect to the electric and magnetic field, the energy will be stored in a given rate itself. So that is what described here. And the negative term describes that this power will be keep on decreasing all the time. So this is what the meaning out of that. By adding this two term, we will get the total power, and that is very well gives the description for the law of conservation. So by this we are describing that, and the second term, which has the conductivity, when this is equal to zero for a lossless medium, obviously there is no power dissipation. In other words, all the total power will be stored by the material itself, which in other words, the wave will be available within that. It cannot escape out of that. That is what the indirect meaning of this. And this multiplication of electric and magnetic field, which we refer as a power vector, and this is often referred as pointing vector. The pointing also has the P, the power also has the P, so which is described by this. And we already know that these two vectors, when you multiply, you will always get another vector. Therefore, the power term will be having its own vector. So how to define that? It is very easy. If the electric field is in the x-axis and the magnetic field in the y-axis, obviously, and the wave is traveling in the z-axis, therefore the power also will be available in the same direction. So power will be having this k axis along the space axis. Okay, the k means space. And we can calculate for a given medium. So we already have a medium, and the medium has sigma, mu, and epsilon, and there exists electric and magnetic field, and both are perpendicular to each other. So that is what described here. Both are actually traveling along the z-axis, and both are varying with respect to time, and they are having their own magnitudes cos omega t. So this is the one form of wave can exist, and that is along the x direction. And corresponding magnetic field, we know that the uh, the magnetic field, the magnitude of the magnetic field will be nothing but the magnitude of the electric field divided by the eta. So that is what it is substituted here, and cos omega t. So when you divide both, you will get eta. And now we have to calculate the power. So in order to calculate the power, we supposed to take the cross product of it. The cross product is always going to give the opposite direction, and they are perfectly perpendicular to each other. There is no angle term between them. So obviously you will get the third axis will be the direction of the power, and you will get always the square of the particular term. And the medium, as of now, the so-called the power is always affected by uh, the magnitude of the impedance. The phase term at this particular case, it is highly negligible, and this could be because the conductivity is equal to 0. And this is the power term. And in order to calculate the power, this is always available with respect to space. So watt per meter will be there. So we have to integrate that. So for this integration, people always take the time average. So this time average is nothing but 1 by t integration over the time for the given case power. So this e square eta and to cos. So this cos square term, it is very well know that we will get always unity when the conductivity is equal to 0, since there is no phase difference between the electric and magnetic field. So you will get only this magnitude term square divided by eta. And this is what in the Kirchhoff's equations also we will get the power is nothing but v square by 2r will come, where here the 2 actually got it by taking the real term alone. So we got this. Otherwise, we will say that it is I square r by 2. So both are same only. So this is in terms of electric field, this is in terms of magnetic field. Like that, we can get the equivalence of it. So for the time average, people always take this two electric and magnetic field, which are complex wave equations. So for any one, we have to take the conjugate, and when you multiply, you will get the real term alone. And however, if there is any other term, can be removed by this selection of only real part. And when you divide by 2, you will get the average power dissipated by the average power available within the given material for a one particular period, it can be calculated. So that is nothing but the power average. And so as I already told, this integration over the time is anyway going to give unity, and you will get this simple average is nothing but e square, sorry, e naught square by 2 eta. But if the medium is not perfect, which means if it is a lossy medium, then the sigma is not equal to 0. If the sigma is not equal to 0, there is no big problem. Eta remains almost same, but there will be existence of the phase term, and the phase term will affect the magnetic field. So if this is the electric field, then the magnetic field, we will see that this in the denominator, you will get magnitude of eta. At the same time, the another phase term will be added, and the negative sign indicate that the magnetic field is lagged by the electric field, and this is actually happening because of the conductivity term. And when you take the cross product of this, then you will get the very similar term, this e square, e naught square by eta, and the loss term has come here. And so we see that this and this two term, when you multiply, you will get 2 alpha z, and the cost term and this cost term. When you multiply this two, you will get 2 terms. This is a very common identity. People use that you can simply take half here and half here. So cos here and this term. So this term is going to tell the change of the phase, and this entire term is going to tell the change in the magnitude. You should always, this is the magnitude of the power term. So this is the we know that this e naught square by 2 eta is going to be because of the lossless medium, and we are introducing the loss here. And one more extra term added here is cos eta. This cos theta or cos theta eta is actually the product has come because of the conductivity. and it is also subject to vary with respect to frequency. And this theta value, when it is, let's say, 0, then you will get the maximum value, of course, which clearly indicate that there is no there is no loss. But as this conductivity keep on increases, then this will keep on going down. For instance, if we have this conductivity is infinite, then we will easily get eta equal to 45 degree, and the term will be reduced very quickly. And that is what we refer as a skin effect. So the skin effect is explained both with the principle of the so-called the wave equation, as well as with the Poynting vector. So obviously in the conductor, the wave cannot enter. In the surface itself, the overall power will be power, all the power will be dissipated within the surface itself. So this is one of the very important reason we always say that in any conductor, particularly any good conductor, you will always see that in the surface only, all the currents will flow, and the power term, heat dissipation, everything will happen within that particular skin depth itself. And within the very inside the metal structure, there won't be any activity. So it is, that is why even Faraday itself told, like, instead of having a solid metal wire, you always take a tube of wire, so that you will get two regions where the electron can travel. So by this you will get twice the current, and therefore you can even reduce the radius of the wire also to achieve the particular current density or anything else you want. But making such a thin wire with tube like structure is very difficult. So even till date, actually, people are using that. But smartly now, people are coming with twisted wires. So you could see that the twisted wires are used now. So that increases the so-called the specific area of the wire. Thereby, we can reduce the radius. And we got nowadays thinner wires while comparing the olden days. This is what we understood out of the Poynting vector. Now we are moving to the next one. So before that, let us take a simple problem. So we are having a non-magnetic medium. The moment you see this words, you're supposed to think about that, because later when you complete this form entire question, sometimes you may forget this. So it is better you can write immediately what is what. So it's a non-magnetic medium. So if it is a non-magnetic medium, then mu r will be equal to 1, and epsilon r is not equal to or greater than 1. So that is what the meaning of non-magnetic medium. And its electric field is available. From the electric field, we can easily extract what is the value of E naught. And so this is going to be omega. So omega is nothing but 2 pi into 10 power 7. So from this, we can easily say that the frequency is equal to 10 power 7. And the time t is there. And then this term is going to be the beta. So beta is equal to 0.8, and which is actually traveling along the z direction. So these are the informations we got it out of the wave equation. And from this, we have to calculate epsilon or eta and the time average power carried out by the wave. So how to calculate that? So, and one more thing we supposed to know here is there is no exponential term with some quantity. So therefore, it clearly tells that the alpha equal to 0. The alpha equal to 0, therefore it means the sigma is also 0, which means it is a lossless medium. Since it is a lossless medium, you can always see that the power dissipation term will not exist the when we calculate the power. So that is what indirectly it means. So now let us work on that. So we already know that alpha is equal to 0 and beta is not equal to omega c, because it is a non-magnetic medium, and the medium is not free space. Still epsilon r is greater than 1, but it is a lossless medium, of course. So we got the beta, and we already know what is omega, and mu is going to be mu naught mu r. Mu r is already 1, so mu is always equal to mu naught. and epsilon equal to epsilon naught epsilon naught. Okay, so these are the things which we have known. And for a lossless medium, we can easily calculate the beta. Beta is nothing but omega root of mu epsilon. So it is very easy to know this. Beta is the very important one. Always you should remember the formula of it. And mu and epsilon, we already have the definition for it. We are going to substitute. And in that, we already know that this root of mu naught epsilon naught is going to be 1 by c. So when you substitute that, you will get it, and you can easily isolate the epsilon r. And omega we know, and velocity we know, and beta also we know, and only thing unknown is the epsilon r. So by rearranging this statement, got this, substituting all the values here and do that. Always, I recommend you whenever you substitute, first you work on the numerator and denominator, then you calculate the remaining values properly. So you can easily calculate the value what you get. So epsilon r is calculated. Then we have to calculate the eta. So eta is for a lossless medium which don't have the conductivity. Obviously, which is nothing but root of mu by epsilon. And mu is mu naught, epsilon is epsilon naught. We are going to substitute all the values. You got it. And we already know that root of mu naught by epsilon is nothing but eta naught, which is the free space impedance, which is nothing but 120 pi. And epsilon r, we already know that root of epsilon r. You can see that the root of epsilon r we already calculated as 12 by pi. When you substitute that, you will easily get the answer. So this is one of the important reason, particularly in electromagnetic field theory. Always you substitute and get some rational number. Then you can reduce that if you need that. Then you can substitute in many other places. So we can easily cancel out, and we will get square of that. We will get the 10 pi square. So we can easily get the value of this. So this medium, definitely it is not a free space. That is why it is showing less than the impedance less than that of 377 ohm. And we can easily calculate the power. Simply you have to take the cross product. And when you take the cross product, you will get all these terms, and the denominator you will get the eta. You have to get the time average. It is very simple that you have to take the magnitude square and the vector you have to define, and the vector is going to be the direction with respect to the wave propagation and this electric field. So the electric field is available along the z direction. Okay, so the wave is actually traveling like this, and it is available in z direction, and it is going to travel in the x direction. So how we found out that it is going to travel in the x direction? The beta x is defining that. So therefore, the next wave, that is the magnetic field. The magnetic field will be definitely available just perpendicular to that. So it will be always perpendicular to the third direction. So the clockwise direction you can take. So that is going to be the y vector. So in this direction only it is going to do that. And so that is that's supposed to be the magnetic field. When you take that, the same direction, the wave propagation direction is going to be the power direction. So the power is calculated. So what you see here is the pointing vector. So you can always the time average power can be asked, or calculate the pointing vector, like that also the questions can be asked. We are coming to the next very important one, that is how this wave will travel from one medium to another medium. So for this, we supposed to recall the boundary conditions which we already solved for the electrostatics. In the electrostatics, we had E1 and E2, and we got two components. One is the tangential component and the normal component with respect to the surface. And then we checked whether it is continuous or not, like that. But in case of the wave whichever is traveling, the perpendicular wave, the electric field and magnetic field, both we can say that it is always transverse to the boundary, and this could be the reason why it is called transverse wave. So at any particular plane of the travel direction, this two waves, the electric and magnetic fields, are going to be available as a transverse component. And because of that, these are going to be continuous. In other words, there won't be any great change in the amplitude. But since these two mediums are different, one is actually the medium one, which has epsilon or mu or different value, and here it is going to have the different value. Therefore, there will be a difference in the magnitude by some other means, and the some other means, it is always referred as the reflection. So in case of the wave propagation, what is not seen in the electrostatics cases, the wave that is actually traveling this direction and it is going that direction, like that, the field is available in this direction, that's all. So when the wave is actually traveling in this direction, and there is a possibility of reflection, and which is very well known, and this is actually could happen in a given medium. We already know that in a particular medium, both the forward and reverse wave can exist, and which is operating in the same frequency with the same phase constant. So that is what often referred as the reflected wave due to the boundary. So this is a special case in the wave propagation, and some amount of energy will be radiated inside the second medium, and that is what we are actually classifying here. We have the primary wave. The primary wave is going to travel along the particular direction. Let's say this is the z direction, and with respect to the z direction, we have a plane. The plane is going to divide the two medium with the medium region 1, region 2, and they have their own quantities. And for instance, we are going to assume these two mediums are having lossless property. Okay. And so this wave is go and going to hit the surface or the boundary, okay, or we can say junction. So this is going to travel along the z direction, and to define, it is going to travel along the plus z direction. We are having E1 plus H1 plus. So the plus means it is traveling in the forward direction. And at this incident, because of the discontinuity, because you will be having two impedances, eta 1 and eta 2. Both are not same. Since epsilon r and mu are not same, you will always get this eta 1 is not equal to eta 2. And because of this boundary discontinuity, we always get the discontinuity in the electric and magnetic field as well. So this is happening by the wave is reflecting in the backward direction. So the wave is getting reflected back, and we got the reflected wave. And to describe that, we always get the negative sign. So you can see that E1 minus H1 minus, the one term 1 indicate that the field available in the medium 1. And some amount of energy is getting inside the medium 2, and we got this. That is what we refer as transmitted wave or the transferred wave. In many of the books, still it is stated as a transmitted wave. So the transmitted wave is described, which is traveling in the positive direction, and its amplitude is described with E2 and H2. Now the question is, what is the relationship between this E1 plus and the E1 minus and the E2 plus? These are the three waves exist in a boundary condition. So what is the relationship between them? So that is what we are going to see. So for this, first we are defining properly how this incident or the primary wave is described. The primary wave is nothing but the basic wave equation to which describes the magnitude and the loss. If it is a lossy medium, we are going to introduce alpha, and the omega, beta, everything is common. Okay. And for simplicity, we are going to say this entire term in the phase form, which is describes with the magnitude and the phase term. And the same thing we can do for the magnetic field. But the only difference between the electric and magnetic field is this eta. So we have it, the denominator eta comes here. Otherwise, all the terms are going to be the same. And to describe the region 1, we are having eta 1. So by this, we have defined this electric and magnetic field for the incident wave. And similarly, we can even calculate for the transmitted wave. For transmitted wave, we get the very similar representation. And to define the medium is 2, we got the 2 here, and the eta 2 also coming into the picture. So eta 2 is the wave impedance of the second region. And the third one is out of this incident, some amount of power is transferred. The remaining power supposed to be reflected back. So that is where the boundary condition satisfies. That is, law of conservation is preserved. And to indicate the reflected wave, you could see that the wave is actually traveling in the opposite direction. If it is minus, you can say it is a forward direction. If it is a plus, it is the opposite direction. And which is indicated again by the sign. And to describe the, it is reflected inside the medium 1 itself. You can see this 1 is available, and the magnetic field is exactly 90-degree opposite, which in other words, that the wave, whenever it is traveling, the electric field, it is traveling, let's say, along the x-axis. Sorry, it is oscillating along the x-axis, and the magnetic field will be available in the y-axis. But the reflected component, where the field will be available same in the x-axis electric field, but the magnetic field will be available in this direction along the minus y direction. So that is why this minus sign is coming into the picture. So we got the all the descriptions for the electric and magnetic field components of the incident wave, reflected wave, and the transmitted wave. Now, what is the relationship between them? So we already know about that. At any particular boundary, we always get continuous transverse component, and these two are transverse component. Of course, we have the direction, and here you have the plane, and this is the normal vector. The normal vector is going to be, let's say, if this is z direction, it is going to be az direction only, and electric field is going to be available x and y direction, magnetic field also. So both are transfer components to that. There is no normal component. So in case of electric field, it is going to be continuous only. And we got this. So the medium 1 and medium 2, both will be having same. And in case of the incident, in the field component, which is available in medium 1, we have two components, the incident component and reflected component. So the addition of both the components is equal to the transferred component. So that is what it indicates that. So later you can easily substitute with another, and the negative sign indicate that this is going to subtract each other with respect to time, as well as the vectorial component. So that is what the result is, nothing but but mathematically they look like adding each other. So you need not worry about that. Next, we have the magnetic component. Magnetic component also transverse component. So since both are transverse component, we are going to make this equal. But when you substitute in terms of electric field, we will use the eta. So these two terms, we are having the we will say incident component, reflected component, and the transmitted component. And this is, we are going to substitute with respect to the same electric field component. So we got this. So you can see that there is a negative sign is coming, which tells that the wave is, the magnetic field is oscillating in the opposite phase. So now we got equation 1 and equation 2. And so both equations are nothing but boundary conditions for electric and magnetic fields. Now, when we subtract this two equation, you will get this new quantity. When you subtract, actually, what generally we do, we take the equation 1, we will multiply with eta 2. Sorry, divide by eta 2, so that you will get this term. Then when we subtract, we can easily remove the transmitted component. We will get only the relationship between the reflected component and the incident component we will get. And when we take the ratio of them, that reflected component divided by the incident component, which is often referred with this new term called gamma, and which is often referred as reflection coefficient. So the reflection coefficient defines that how much amount of electric field is reflected back due to the boundary means boundary condition or the difference in the impedance between the two mediums. And you can easily see this expression, which is very easy to remember. You can always say that eta 2 minus eta 1 divided by eta 1 plus eta 2. So in the numerator, we are subtracting. In the denominator, we are adding two medium impedance, not opposite. We can't do with eta 1 minus eta 2 like that. We should not do that. It is always eta 2 minus eta 1 divided by eta 2 plus eta 1 like that. And that is what we refer as the reflection coefficient. So the in a particular boundary, we have two medium with eta 1 and eta 2, two mediums, and one wave is actually traveling and incident upon that. And when it is incident upon that, there is some amount of power or amount of electric field alone getting reflected. So this is we are calling as incident wave, and this is we are calling as the reflected wave. Both the ratios are described by the reflection coefficient. Now we can a similar way when you add this two equation. When you add this two equation, you can see that there is a subtract sign is the negative sign. So when you divide by eta 1 and when you add this two equation, you will get the reflection term will be removed. You will get purely incident reflected term. You can get the ratio between them. So when you take that, when you rearrange that, you will get a new quantity, and that ratio is often referred as the transmission coefficient. Like how it is called reflection coefficient, this will be called as transmission coefficient, and this is going to be this. And this term and the reflection coefficient, they are highly connected. When you add one with the reflection coefficient, you will get the transmitted power. So that is what you get it here also. Here also very similar description is there, that when you divide this entire term by the E1 plus, you will get E1 plus, here also E1 plus. This is going to be the gamma, this is going to be the tau. So both are highly connected. And interestingly, there is some special case that if the second medium has the impedance equal to 0, that means it is a perfect conductor. Perfect conductor also should have its own magnetic field, but still, if the second material is absolutely zero impedance, then we know that there could not be any existence of the reflected term. Why? Because the reflection coefficient will become 1, that too with negative sign, which means that all the power, whichever the incident power, will be simply reflected. You will get this E1 minus is equal to E1 plus will come, and there is no power or there is no energy transferred within the medium 2, which is having impedance 0. And so this very simple reason is it is going to be the perfect metal. So it is like a perfect metal is mirror for a electromagnetic wave. So if there is a perfect conductor, whatever the wave is coming, it will be simply reflected. Nothing went inside. So that is why people always refer the good conductor will be having electric field equal to 0. If the electric field is equal to 0, it is applicable to both wave time dependent and time independent field components. And for these components, we can even calculate the power. And so the power, for this power, you can easily say that with respect to the incident component power, the reflected component power is having the ratio of gamma square, which is nothing but the reflection coefficient square. So if you know about E1 plus from this, by having the values of eta 1 and eta 2, you can calculate E1 minus. Then from this eta 1 and eta 2, you can, for this we need this gamma, and for E2 plus we need tau. That also once again can be calculated from this E1 and E2, and we can take the square divided by eta 1. You will get the power term V1 plus, and you can calculate this P2 plus and P1 minus. The reflected power, transmitted power, for the incident power, everything can be calculated. So you can get it like this. So these are the power, means how the power is dissipated or the power is stored in two different mediums. and what is the continuity between them. So that also described here as a aspect to this. So by this, I believe we got it. And we have one small two problems. These two problems you will see in the next class. I'm sorry I have taken extra time. I'm sorry for this. Thank you. So whatever the questions we have, I will answer in the next class. And I